Okay, here we're going to look at how to multiply double-digit numbers, looking at breaking them into groups using an array as our first main method of solving, and then we're also going to look at using the algorithm for those of you that prefer that method. To first show how we can use the idea of an array to solve a multiplication with larger numbers, we're going to use the example 17 groups of 13, or 17 times 13. So what we can do first of all is just draw one group of 13. So the bar shown on the screen shows 13 squares in a row, and I've just put an outline around those so it's one row of 13. I can then draw 2 rows of 13, 3 rows of 13, 4 rows and so on, all the way until I have 17 rows of 13. And that just helps us understand exactly what it is that we're multiplying. We're multiplying 13 17 times. And of course, another way we can describe this is 17 groups of 13, or 17 times 13. Now to solve this, I could simply go and add 13 plus 13 plus 13 and do that over and over and over again, as you can see in the diagram. Or I could skip count by 13s. But better yet, I would probably wish to choose an amount that I can multiply confidently and quickly. So to do this, I would choose 10 groups of 13, which I've coloured in with green. So here I've got 10 rows that I've coloured in, and I've chosen that because I feel confident with my 10 times tables, and I feel that I can solve 10 times 13 quite easily. With the remaining groups, so I have 7 groups remaining of 13. With those remaining groups, I would then choose another grouping that I'm confident with. In this case, I would choose 5 groups of 13. Again, because I'm confident with my 5 times tables, and particularly because I can see that 5 groups of 13 will be exactly half of my green area of 10 groups of 13. So once I solve one, it's going to help me solve the other. And with the remaining 2 groups, I will just solve those as a simple double, being confident again with 2 times 13 or double 13. So to solve these, 10 times 13 is one I should be fairly confident with. If I had to skip count by 10s 13 times, I'd get to 130, but it's one that would mostly feel confident with knowing. 5 groups of 13 would be half of 10 groups of 13, so in this case is 65. I probably would be avoiding skip counting by 5s for something as simple as 5 times 13. However, 5 times 12 is 60, so I might use that fact to get me to 65 as well as an option. And 2 groups of 13 is just 13 plus 13 is 26, and again that one's a double. Once I've got these different shaded areas solved, then I just simply add these 3 numbers together, and that will give me 130 plus 65 plus 26. I'd add my 130 and 65 first to give me 195. Then I'd add on my 26. And you can see there I've done a bit of a shortcut. I've added my 6 on first to get 201 and then the remaining 20. How you do your addition, shortcuts and strategies is entirely up to you. That's just one example of how you can do it. Of course, 221 being the answer. Now, if I remove all the workings we've just done and just bring us back to the large rectangle that we started with, we can see this is still going to be the 17 rows of 13. I just haven't individually put lines for each row. Doing it this way, I can quite simply draw on the areas that we just solved. So if you actually look closely or pause your screen, you'll still see that it is 10 rows with 13 going along each row. For the red section, there are still only 5 rows in the green section, and each row is 13 long, and 2 rows each 13 long. So there is no need to actually draw each individual row or your entire array row by row, as long as you're aware of what you're working with. And again, solving those areas and adding them together is the method that you'd use, and you could use an algorithm for addition if you pleased. Now, for those of you that are preferring the idea of using the algorithm, I'm going to step you through that right now. Before I do so, I want to point out a few things. One, the algorithm is extremely useful because it can be used for absolutely every multiplication, and it is a rule-based system that will always work. There is also some risk involved with using algorithm in that you need to make sure you are understanding the maths that's going on, because if you do make a simple mistake, it's very easy to do and easy to miss and then end up with the wrong answer. So as I step through the algorithm on the screen today, I will be using the diagram that we've used for the first example so that you can see what's actually going on within the algorithm. So to begin the algorithm, it's very important to put your numbers directly and above and below each other. So in this case, we've got 17 times 13. The 13 sits directly beneath the 17, and it's important that you have your place value positions lined up. So what I mean by this is that your ones column is in line and your tens column is in line. So the 3 and the 7 in 17 and 13 are in the ones column, and they're directly above and below each other. And the 1 in 17 and the 1 in 13 are both in the tens column, and they must be directly above and below each other. Then, when you're using the algorithm, you follow a simple procedure, and you start in the bottom right corner. So the bottom right corner is the number 3, and so you would multiply the 3 first going directly up, shown by the red arrow, so it becomes 3 times 7. So that 3 times 7 is shown in the diagram in the box that I have showed in light blue. Here we can see that I've actually also sideways written 3 groups of 7 because that's the direction that those groups of 7 are shown in the diagram, and they would be 21 altogether. So if you actually paused your screen and had a look, in that rectangle you actually have 3 rows of 7 grid squares, and there are actually 21 grid squares sitting there. So the answer there is 21. Now the way that you record this in the algorithm is you would need to put the 1 from 21 in the ones column, because the 2 from 21 actually stands for 2 tens. Now the 2 tens would go in the tens column, and we can do a shortcut here and just put that 2 above the tens column for something for us to remember to add on when we're finished using our 3. So this is where the algorithm can be a little bit confusing. So essentially we are going step by step through. We're going to do 3 times 7. Then in a moment we're going to do 3 times 1, which is 3 times 110, shown with that arrow there. And then we're going to solve that, and we can add our 2 tens on once we've solved that section. So in this case, you can see it drawn in the rectangle, and I've written the groupings sideways once again. It's 3 groups of 10 equals 30, which is where the 3 times 1 comes from. So remembering when we're doing 3 times 1, it's in the tens column, so it's actually 3 tens. And then we add on our 2 tens, so that would actually give us 50. So it would become 51 underneath. So to repeat that again, because it can be a little bit confusing, what we have done is we've done 3 times 1 plus 2 equals 5, and that's where the 5 is coming from in our algorithm on the left. However, we're remembering that we are actually doing 3 times 110 plus 2 tens is 5 tens. Therefore, it's 51. Now we'd be moving on to the next part in the algorithm. We've finished multiplying our 3 because we've multiplied it by the 7 of 17 and by the 1, 10 within 17. So now we're moving on to the 1 in 13. So that's 110 times 7. And again, I've done an outline of the part of the array that we would be looking at here. So here we're doing 10 groups of 7 because the 1 is actually 110. So if we write that out, it would be 10 times 7 equals 70. Now to record that, it can be a little bit confusing. We put 70 down because that's what the answer is, But if you're reading it as 1 times 7, you could easily make a mistake and put a 7 under the 1. So some people like to follow a rule of putting a 0 down and then doing 1 times 7 and then putting the 7 next to it. However, for better understanding, I'd much prefer you to think of it as 10 times 7, or 110 times 7 is 7 tens. So you're needing to put your answer in the tens column. Then your last step is the 1 times 1, which is going directly up. But again, we need to be remembering that we're actually doing 10 times 10, because it's 110 times 110. Okay, so 10 times 10, of course, is 100, and it's shown in the diagram on your right as the last section. And when we multiply 1 times 1, we get 1. And that would go into the hundreds column because it is actually 10 times 10. So although the algorithm is quite straightforward, it can lead to confusion, as I'm sure is coming through in the way I'm running through the method. Once we've completed all these steps and found an answer, we then we haven't found the answer, we've found two answers in 51 and 170, we now add those together. So essentially, we're adding together the two sections that we've solved. So in the diagram, you can see there's 4 sections, but we were actually adding 2 of them together each time. So when we did the first 2 rectangles, we got 30 and 21, and we were adding them as we moved along, and we got 51. Then when we solved the next 2 larger rectangles, we had 100 and we had 70, and we solved that as we went along, and we got 170. Now we add those 2 together, and we can do that using the addition algorithm, if we please. So we could do 1 plus 0 is 1, 5 plus 7 is 12, and so that means 12 tens, so 2 tens in the tens column, and then the 10 tens would be 100, so that becomes a 1 in the hundreds column. So 100 plus 100 is 200. And we get the same answer from the beginning, 221. So of course this method works just as well as the method using the array model. Now the closing idea I want to leave you with, however, is if you look at the diagram that I broke into sections as we solved the algorithm, you might notice that it matches the steps that we did within the algorithm. However, it also shows the only way that you can break the array using the algorithm. So what I'm trying to say is the algorithm will take you step by step through breaking your array into pieces and solving them and then adding them together, but you will not have any choice in how that's going to happen. You will just have to follow the steps. So in this case, you just have to do 3 groups of 7 and 3 groups of 1, followed by 1 group of 7 and 1 group of 1. You have no choice over a more efficient way or a shortcut or any other method you wish to do. So when you think about the first method we did, and if I can quickly scroll back to it, you can see I broke it up into what I thought was a much quicker and more efficient way. And you can see I just put it into 3 big chunks that were not only quicker to solve because there's only 3 of them, but they were much easier times tables to solve. And there's nothing stopping me from breaking them into totally different shapes, depending on what my preference is. So if I happen to know 16 times 13 because I'm an expert on 16 times tables, there's nothing to stop me solving that and then adding 13 on, or whatever the case might be. So it's just something to keep in mind, that the algorithm is very useful. It's something I would strongly recommend, especially when the numbers become very large and fiddlesome. However, where possible, I'd be looking for creating my own array and breaking it up into times tables that I find the most efficient.